Here we're told we have a hydraulic accumulator. These are used to reduce pressure pulsations in a machine tool hydraulic system. So basically the idea is that if there's a sudden change, for example, in the oil that's cycling through the hydraulic system, rather than that sudden change being pushed all around the system and causing perhaps some large pressure spikes, this container can absorb that because the level of the oil can move up or down as needed. These sorts of things are also used in house system, just a plumbing system within a house to help reduce what's called water hammer. So when someone suddenly turns on, or usually it's when they suddenly turn off the faucet in a house with a plumbing system, if they don't have this kind of device somewhere in the plumbing system, then you can get what's known as water hammer. You get a sudden pressure spike because of the quick closing of the valve that can move through the rest of the system, and that can cause some damage to the pipes. So having just a little bit of cushion somewhere in the system, that's really essentially what this is it's allowing some cushioning. The water level here can change up or down to absorb those sudden changes in flow rate or pressure spikes, so they don't travel around the whole system. So anyway, that's the purpose of this thing. But we're told that we're given, for the instant shown, we're given the volumetric flow rate. This is in gallons per minute coming into this accumulator. We're told the average speed of the oil coming out of it, and it's coming out through this pipe with a diameter of 1 1/4 inches. And we're asked to find the rate at which the accumulator gains or loses oil. And so we're going to find the change of mass of the oil inside here as a function of time. We're also told that the oil has a specific gravity of 0.88. Just for your reference, specific gravity is defined as the density of whatever liquid divided by the density of water at 4 degrees C. This is a nice temperature because the density of water is 1,000 kilograms per cubic meter. So the specific gravity is just a way to find the density of something easily. So the density of the oil here, if its specific gravity is 0.88, that means the density of the oil is 880 kilograms per cubic meter. Okay, so you don't need to know that for thermodynamics 1. You don't need to know this definition. It's more of a fluid mechanics topic, but it does, it's fine. I can just present it here to you. It's just a way to find what this shouldn't be the specific gravity of the oil. It should be the density of the oil. Okay, so anyway, we're trying to find the rate at which oil accumulates inside this device. So I'm going to draw a control volume that surrounds the interior of the device. And then we're going to apply conservation of mass to that, because I'm trying to find how the mass inside there changes with time. It's this dmCv/dt term that I'm trying to find. So the time rate of change of oil mass within the control volume is equal to the rate at which mass comes in minus the rate at which mass goes out. And this is what I'm trying to find right here. The rate at which mass comes in, we're given it in terms of the volumetric flow rate. So this will be just the density of the oil times that volumetric flow rate coming in. And then over here at the outlet, we're given the diameter and velocity. So the mass flow rate going out will be the density of the oil times the velocity going out, that's the average velocity out, times the area out. So we're given a diameter, so to find the cross-sectional area would be the pi diameter squared over 4. Okay, so that's how we can find this. So we know the density of the oil. We can find that here, for example. Well, I guess we're given this in terms of English units in the problem statement. So you can find the density of the oil in English units, do that conversion. It comes out to be 1.71 slugs per cubic foot. Doing this in terms of slugs rather than pounds mass. It's fine. You can do it whatever set of units you want. The Q in, we're given as 5.75 gallons per minute. And then the average velocity out is 4.35 feet per second. And the diameter out is 1.25 inches. So you'll have to do some unit conversions to get these all in a consistent set of units, but if you do all that, you'll find that the time rate of change of mass inside that control volume comes out to be minus 4.15 times 10 to the minus 2 slugs per second. So the accumulator is actually losing oil in these under these conditions. It's the level of the oil here would be going down, for example. So this is a pretty straightforward application of conservation of mass. It's just applying conservation of mass to a control volume surrounding the accumulator tank, recognizing that we're given a volumetric flow rate coming in. So to find the mass flow rate coming in, it's just density times that volumetric flow rate. At the outlet, you find that mass flow rate going out by taking the density times the average velocity times the cross-sectional area, which in this case is found as the equation of the area of a circle. Probably the hardest thing by far in this problem is just having to deal with unit conversions here. So I'm not going to go through that part. Hopefully you can do unit conversions on your own. Okay, we'll end the example there.